the last session, we've been talking about the group of field over a subfield. Group of field over a subfield. If F is a subfield of E, the group of all automorphisms is equal to the group of all automorphisms on E that leaves F fixed. What we are going to do today is we'll do some examples on this. So, and before we start, I want to refresh a couple of theorems we established earlier. The first one is a field is either of characteristic P for a prime P and includes a subfield isomorphic to ZP or of characteristic 0 and includes a subfield isomorphic to Q. Meaning any field, whether it is finite or infinite or any kind of field, there is a field either it contains its subfield isomorphic to CP or it contains its subfield isomorphic to Q. In this case, the characteristic is P. In this case, the characteristic is 0. Any field. That's a very powerful result we established earlier. The second one is, let F bar be a closure of a field F and alpha belongs to F bar be algebraic. Then any isomorphism from alpha, the simple extension of alpha, to a subfield of F prime, F closure, maps alpha to its conjugate. And the third one is again let f prime be the closure, there's only one closure of f, and alpha and beta are conjugates, then there exists one and only isomorphism that maps alpha to beta. So we are going to use these three results which we established earlier to come up with some examples on group of a field over a subfield. So we are going to use this scenario. So see, if you consider any infinite field, then Q is always a subfield of that field, always. So it's a good idea to start with Q, because you are going to have a lot of fields that contains Q. All infinite fields contains Q. So let's start with this very trivial example. Let us see what is a group of Q over Q. So this should contain automorphisms. So what does this mean? This means that all automorphisms on Q that fixes Q. And that means what? There is only one automorphism where I is the identity of them, where I is the identity automorphism. So there is only one. So that is very trivial. But I want to find out what are the possible automorphisms on Q, whether it is fixing Q or not. Is there any other automorphism? Let's see. What is Q? Q is equal to P by Q, where P and Q are integers and Q not equal to 0. By the way, I just forgot to mention one more term. Any field contains either CP or Q. Any field. So these two fields, ZP and Q, are also called prime fields. Prime fields, okay? That is just a terminology that I missed it earlier. So just want to mention it again. So yeah, P and Q are integers where q is different from that is a collection of all rational numbers. Now let phi to q be an automorphism. Meaning it's a 1 1 and on to homomorphism from q to q. So there are two conditions here, three conditions. Let p by q is equal to 0. That means p equal to 0. That implies p by q is equal to 0. No doubt. And let p by q is greater than 0. That will imply what we are going to do is both p and q greater than 0. Either way is fine, but we are going to take it further side. So what does this mean? So let us compute phi of p by q. Because it is an automorphism, that is equal to phi of p by phi of q. And this is an integer. So this you can write it as phi of 1 plus 1 plus dash dash 1 p times over phi of 1 plus 1 plus dash dash plus 1 q times. And that is equal to phi of 1 plus phi of 1 plus dash dash phi of 1 p times phi of 1 plus phi of 1 plus dash dash phi of 1. This is p times, this is q times. So this is actually, each of them is 1. So this is actually p by q. This is any automorphism. So phi of p by q is equal to p by q. Now let's take p by q less than 0. That implies p by q is equal to 0 minus p1 by q1, where p1 by q1 is positive. And that is equal to, okay, so we can apply the same rule. Phi of p by q is equal to phi of 0 by p1 by q1, that is equal to phi of 0 minus phi of p1 by q1, where p1 by q1 is positive, that is equal to 0 minus p1 by q1, and that's equal to p by q. So either way, if you take in any situation, phi is an identity map. So the only automorphism on q is the identity automorphism. This is not a part of our finding the group, but I just want to mention that in a prime field, in Q, the only automorphism is the identity automorphism. I'll do another example. Let us find out the group of Q of Q root 2 over Q. So this is q root 2 and there is a q here. So we want to find out all the automorphisms from q to q of root 2 to q, leaving q fixed. So let us consider the conjugate isomorphism. So, by the way, q of root 2 and q of minus root 2 are same. This is because the definition of the elements of this is a plus a plus b root 2. Here it is a minus b root 2. A and b are q. So minus and plus doesn't make any difference in q, because here if it is 3 root 2, b is 3. Here then b is minus 3. So those are same. So these two fields are one and the same. And if you consider the conjugate map 0 2 comma minus root 2, that is from q of root 2 to q of minus root 2, and basically that is going to be an automorphism. And what is the definition of this? A plus b root 2 is equal to a minus b root 2. This is the definition. So conjugate isomorphism is an automorphism here. And let us see what is this mapping of elements of Q. So psi of just A, this is from Q, is equal to A. With this definition, for all A belongs to Q, implies psi of root 2 comma minus root 2 leaves Q fixed. So one element is I and the other element is psi of root 2 comma minus root 2. My question is, do we have any other element? That is where we are going to use these two. See, when we say isomorphism, any isomorphism from F alpha to a subfield of F closure maps alpha into its conjugate, means this subfield is actually Q of root minus root 2, which is same as Q of root 2. So alpha, here it is root 2, has to map to minus root 2. That's what this says. And for alpha and minus root 2, there exists only one isomorphism. So that means it cannot contain any other automorphism. So this is the only automorphisms that leaves Q fixed on Q of root. Meaning, if you have any other automorphism, what this should do? Suppose there is another automorphism that should map root 2 to minus root 2. So that means it could be this. But the map isomorphism which maps q root 2 to minus root 2 is unique. So we cannot have anything else. So let us assume that there is another automorphism, say sigma from q root 2 to q root 2. So that means sigma should map root 2 to either root 2 or minus root 2. And there exists only one map each that maps root 2 to root 2 and root 2 to minus root 2. That implies sigma should be either I or psi of root 2 minus root 2. So this is the complete set of all automorphisms that leaves Q fixed. Now let us consider one more example. Let us take Q of root 2 comma root 3 let us try to find out the group of Q of root 2 comma root 3 over Q. So here also it is like this. This is our Q root 2 comma root 3. He is our Q, and we have a Q root 2 here, and we have a Q root 3 here. This is a subfield containing Q, and this is a subfield containing Q and root 3. Again, any automorphism, this definitely contains I, no problem. Any automorphism on G root 2 comma root 3 should map root 2 to root 3, root 2 to root 2, or root 2 to minus root 2, and root 3 to root 3, or root 3 to minus root 3. So what are the elements of this? Q of root 2 comma root 3 is equal to A plus B root 2 plus C root 3 plus D root 6, or combinations A, B, C, D belongs to Q. And combining these two conditions, let us take a sigma here from Q of root 2 comma root 3 to Q of root 2 comma root 3. The whole automorphism is determined by root 2, root 3 and root 6 and of course 1, because those are the base elements. 1, root 2, root 3 and root 6 are the base elements if you consider as a vector space of Q of root 3 comma root 3, root 2 comma root 3 over Q. So what are the types of automorphism we can have? This can be one of this. Actually I am not going to consider I. So sigma 1 of A plus B root 2 plus C root 3 plus D root 6 equals to A. I'm going to consider this scenario: minus B root 2 plus C root 3 minus D root 6. Of course, sigma 1 leaves Q fixed. So we can write it as and sigma 1 leaves Q fixed. So this is one of the candidate. No problem. Second one is root 3. So let's take A plus B root 2 plus C root 3 plus D root 6 equal to A plus B root 2 minus C root 3 minus D root 6. And sigma 2 leaves Q fixed. So this is also another candidate. Is there any other candidate? Maybe or may not be, but composition of any two automorphisms is another automorphism. See, in the previous case, you have only 1 and sigma. And if you take the combination of this, it's again sigma. So that is why we didn't even go to the composition here in the previous situation. Here we have two non-identity automorphisms. So we can always think about the composition of these two. If you take the composition of these two, and if it is not I, that could be a candidate of an automorphism in this group. So what is sigma 1 after sigma 2? Of A plus B root 2 plus C root 3 plus D root 6 equal to sigma 1 of, this is actually A plus B root 2 minus C root 3 minus D root 6. And that is equal to, wherever you have a root 2, replace with minus root 2. A minus B root 2 minus C root 3 plus D root 6. So this mapping is not available in anywhere. So we can consider this as another automorphism. See, if you consider this situation, every automorphism should map 2 to root 2 or 2 to minus root 2. See, sigma 3 is mapping root 2 to minus root 2. So this is perfect. And sigma 3 maps root 3 to minus root 3. So this is also perfect. So there are 3 different automorphism. Of course, we can always find, see we have one, again this one, we can always find out whether sigma 1 of after sigma 3, sigma 2 after sigma 3, we can find it out. But see, sigma 1 square is equal to I. We already proved this one. The order of sigma 1 is I, and order of sigma 2 also is equal to I. So if you take the combination with sigma 3, which has already sigma 1 and sigma 2, this is not going to create another automorphism here. So this is the only automorphisms in that group. Okay. I want to introduce one more automorphism on a finite field. It's called Fraubenius automorphism. Let F be a finite field. If it's a finite field, definitely its characteristic should be a prime number of characteristics P a prime number and that implies Cp is a subfield of F. So we're talking about a field here and a subfield here. And we are going to define a map from, or let's say, map from F to F by phi of A is equal to A to the power of P. A belongs to F. For all A belongs to F. This is just a map. So we need to prove that this is an automorphism. If we want to prove that this is automorphism, first we need to prove that this is a homomorphism. So, but one result we are going to borrow from the previous theorems are A plus B to the power of P to the power of n is equal to A to the power of P to the power of n plus A to the power of B to the power of P to the power of n. I'm not going to prove this here, we already established this earlier. This is because F is of characteristic P. If you do the binomial expansion, the terms within these two all will be zeros. That's why this is. So this is the result we are going to use to prove that this is a automorphism. So this implies that A plus B to the power of P is equal to A to the power of P plus B to the power of P. Now let us take two elements for all A comma B in F. So let us take A comma B belongs to F implies phi of A plus B is equal to A plus B whole to the power of P by the definition, and that's equal to A to the power of P plus B to the power of P, and that's equal to phi of A plus phi of B. And that is how you prove homomorphism, and you need to do for the multiplication also. This implies phi of AB is equal to AB to the power of P is equal to A to the power of P times B to the power of P is equal to phi of A times phi of B. So that implies phi is a homomorphism. Phi is a homomorphism. And what we need to do is we need to prove that this is a 1-1 and onto. F is finite, so it is enough if you show that it is 1-1. In any finite mapping, if it is 1-1, finite mapping to itself, if it is 1-1, it automatically becomes onto. So how do you prove if a homomorphism is onto? Take the kernel of this. The kernel of phi is equal to A belongs to F such that phi of A is equal to 0, and that is equal to A belongs to F such that A to the power of P is equal to 0. So that is actually equal to 0 because A is coming from a field. So it is definitely an integral domain. So this is 0. And that implies phi is 1-1. That implies phi is onto. This is because F is a finite field and phi is from F to F. So if it is 1-1, it has to be onto. So that means phi is an automorphism on F. Let us see whether it fixes ZP. F. Okay, so let C belongs to ZP. What does that mean? That means phi of C is equal to C to the power of P. But that is, C is from CP. So that is actually equal to Z. Because what is ZP? ZP is equal to 0, 1, 1, P minus 1. So if you take any element here to the power of P, that is going to be C. Because it's a cyclic group. So this implies phi is an automorphism on F leaving CP fixed. Leaving ZP fixed. So this actually belongs to this Fraubenius automorphism belongs to G of F over C. We need to do one more result on this. Now, our definition of this Fraubenius automorphism is A is equal to A to the power of P for all A in F. And we know that ZP is a subfield of F. Now let us take an element from CP. And that we know that Cp to the power of P is equal to C, and that implies Cp minus C is equal to 0, and that implies C is a 0 of x to the power of P minus x in Zp of x. x to the power of p minus x has at most p has at most p zeros, right? It cannot have more than p's. It cannot have more than p zeros, and every element in ZP, how many are there? P elements. Right? Are zeros of x to the power of p minus x, because C is any element from here. If it is in CP, then it is a zero of this. That means all elements of ZP are the zeros of x to the power of p minus x. So let us evaluate our f over the fixed field of f for this Fraubenius automorphism. What does this mean? This means that the elements from F such that phi of x equal to x. And what does that mean? This equal to elements of x belongs to F such that this is x to the power of p is equal to x. And what is this? This is actually the zeros of xp minus x. This is actually zeros of xp minus x. So all elements, all zeros of, this is equal to all zeros of xp minus x. And what is that? That is equal to ZP. So the result is the fixed field of Frobenius automorphism is CP.